If you add thermal energy to an object, it is going to heat up and increase its temperature. The amount that its temperature increases is related to how much of the object you have, what its mass is, and what the nature of the material is going to be. We talk about that nature of how easily a material can change its temperature. That is known as specific heat. So in this video, we're going to talk about this property. To get to this, let's first just look at generic terms to define this: conductor and insulator. In electricity, we talked about conductors and insulators based on how easily it was for electrons to flow through them. Well, there's a similar sort of conversation here in thermal physics. In thermal physics, a conductor is how easy, or a material that is very easy for thermal energy to flow through as heat. For a pan, the conductor is the metal part of that pan. It's allowing the heat to flow from the stovetop into the food that you're trying to cook. An insulator is a material that transfers its energy poorly, and by design, the handle of this is an insulator. Plastic is a very good insulator. Rubber is a good insulator. Also, the insulation that's used in your house, like fiberglass and air, is a good insulator that doesn't allow heat to travel through very easily. Well, we can define this a little bit more quantitatively by talking about specific heat. Specific heat is the amount of energy required to raise the temperature of 1 kilogram of a substance by 1 degree Kelvin. If we look at an example, copper has a specific heat of 390 joules per kilogram per Kelvin. This unit looks kind of scary at first, but it is just the same thing as this definition. It's got the definition baked in. It's 390 joules required for 1 kilogram of copper to increase its temperature by 1 degree Kelvin. I also want to note, as we saw in the last video, that Kelvin has the exact same increments as Celsius. So increasing by 1 degree Kelvin is the same thing as increasing by 1 degree Celsius. The increments are equal to each other. So let's look at a table of these specific heat values. And you can see that it varies from material to material. The lower the number is, the less energy it takes to heat up that object. So if we look at this list, which substance from this list takes the most energy to heat up? Well, there's one material here that by far has a larger specific heat, and that is water. Water has a specific heat of over 4,000 joules per kilogram per Kelvin. It is one of the reasons that you get a lake effect. If you live by a lake, your winters aren't as cold, your summers aren't as hot, because the water works as a giant heat sink, that it takes a lot of energy to change its temperature. So on hot days, the water stays colder. It doesn't become as hot very quickly. And on cold days, the water stays warmer and kind of equalizes the weather around it. In this list, which substance takes the least energy to heat up? Well, that's the one with the lowest specific heat. And in this list, that object is lead. This list is not exhaustive, but it gives you an idea of some of the range that you might see in these values. If we were to compare two values, you should be able to find them on the list. If I were to ask you which metal, in this case, heats up faster, assuming you have the same mass of metal, will aluminum or iron take more or take less time to heat up? Which one will heat up faster? Finding these on the list, aluminum is 910 joules per kilogram per Kelvin. Iron is 448 joules per kilogram per Kelvin, which means that iron should heat up faster. It takes less energy per kilogram to increase by 1 degree Kelvin. So if you have the same amount, it should increase twice as fast. So that brings me to a question. I have upstairs in my kitchen 2 different pans. I've got an aluminum skillet and an iron skillet. My aluminum frying pan heats up way faster than my iron skillet. We saw earlier that the specific heat of the aluminum is higher than the iron skillet. So why do you think the iron takes longer to heat up? Well, the reason is these aren't the same mass. That this iron skillet is significantly heavier, so it actually requires more energy overall to increase its temperature, even though per kilogram it takes less energy, just more of it. So if we want to define this in terms of a mathematical relationship, we can relate this mass, specific heat, and temperature all together to talk about the heat energy that is being transferred. This is the equation that we'll be using, and is one of the most important equations for this particular unit. Let's define the different variables that are here. Heat energy is represented by a Q. Q is not the most obvious representation here, but you're going to see that quite a bit. This is just an energy. So as with every energy that we've talked about before, heat energy is in terms of joules. Now mass, represented with an M, is always going to be represented in terms of kilograms here. Specific heat, we're going to use a lowercase c to represent. And that, as we saw before, is joules per kilogram per Kelvin. And change in temperature is this delta T, the delta representing a change in, and capital T representing its temperature. And that can be represented in either Kelvin or Celsius. The reason that this can be either is, again, because there are 100 degrees between water boiling and water freezing, so their increment size is exactly the same. So if we are looking at a change in temperature, the change in Kelvin is the same as a change in Celsius, that you can use either in this particular case. So looking at a couple examples, if we want to solve how much energy is needed to increase the temperature of 0.755 kilograms of iron by 20 degrees Kelvin, we first need to figure out what the specific heat of iron is. We need to know C in order to calculate MC delta T to calculate Q. So if we plug everything in, 0.755 times that 400 joules per kilogram per Kelvin times 20 degrees Kelvin, that's our delta T, how much we're increasing it by. We can calculate Q is 6,765 joules. So again, Q is energy. That's how much energy was added to the system in order to increase its temperature. If instead we're looking at how much energy must a refrigerator absorb from 0.225 kilograms of water to decrease the temperature of this water from 35 Celsius to 5 degrees Celsius, we first need to figure out a couple different things here. Water has a specific heat shown by this table of 4,180 joules. We know the mass, and we can find this change in temperature. In this case, the temperature goes from 5 to 35. So the change in temperature is actually a negative 30. And because of that, one way that we can define this is by a negative heat, negative amount of energy, because that energy is being lost by the water. So typically we don't talk about energy in terms of positives and negatives. We would never say that an object had negative kinetic energy. But in this case, that's a really useful way to define that. We say that this water is losing 28,000 joules of energy, and because of that, the refrigerator had to absorb that energy to remove it from the system. So those are some more simplistic examples of the specific heat calculation. Really just plug and chug, just figuring out M, C, and T. It can be a little bit more complicated though as well, because a lot of times you're not given these exact values, and you have to figure out these values from other things that you know about the system. So if we are told that air has a density of 1.3 kilograms per cubic meter and specific heat capacity of 1,000 joules per kilogram per Kelvin, if 500 kilojoules was transferred to a room of 80 cubic meters, what was the temperature rise? So again, we are given here 500 kilojoules. Kilo is just 1,000. So Q, the heat energy that's transferred to the room, is 500,000 joules. Something else that I know the specific heat capacity is C, 1,000 joules per kilogram per Kelvin. And then typically I'd also want to know the mass if I want to figure out the temperature rise, but I'm not given a mass. I'm not given kilograms outright. Instead, I'm given a density of the air is 1.3 kilograms per cubic meter, and the volume of the air for this room is 80 cubic meters. So if I know that there's 80 cubic meters and each one is 1.3 kilograms, I can calculate the mass, just the density times the volume. So 1.3 times 80 is 104 kilograms. So now I have enough to really use this equation. Rearranging for delta T is Q over MC to find that there's a delta of 4.81 degrees Kelvin, which is again the same as 4.81 degrees Celsius. So Given the amount of energy that's provided, I can figure out how much, on average, the temperature is going to rise throughout that room. I can also look at this in terms of power. Power is something that we saw very briefly earlier on this unit. Not this unit, but earlier on this year. And that's usually measured in watts. So here, I'm given how long will it take a 2.20 kilowatt kettle to raise the temperature of 800 grams of water from 16 degrees Celsius to its boiling point if the specific heat capacity is 4,180 joules per kilogram per Kelvin. There are a lot of pieces to this that were not given straight from this Q is equal to MC delta T sort of equation. So let's figure out what we have here. Well, this is the equation that we ultimately want to use because we want to know how long. That doesn't really tell us how long, but it's going to tell us how much energy is there. So we can use this power and energy to help us eventually figure out a time. So if we know that the mass is 0.8, that's the number of grams converted into to kilograms. The specific heat is 4,180, and the temperature change is going from 16 degrees Celsius to its boiling point of 100. Our change is 100 down to 16. We know that there are 280,896 joules of energy that need to be added to the water to get it to boiling. This kettle is producing 2.2 kilowatts. 2.2 kilowatts is the same thing as saying 2,200 watts, which is the same thing as saying 2,200 joules per second. Power is just work divided by time, or joules divided by seconds. So 2,200 joules every second, and I want to produce this many joules, 2,800 or 280,000 roughly. So I just have to convert that so it's in seconds. 280,896 divided by 2,200 joules per second ends up giving me 128 seconds. So roughly 2 minutes of energy being added to the system in this 2.2 kilowatt kettle to ultimately raise the temperature of the water the amount that I'm looking for. So finally, let's talk about how heat can be converted from one place to another. One way that we do this in an experimental setting is by using something called a calorimeter. A calorimeter is basically just an insulated environment so that heat isn't gained or lost by the surroundings. That the only heat transfer is what's happening inside this thing. And it can be as simple as a styrofoam cup and a nice lid that insulates that from its surroundings. So in this case, you can figure out from how much water is in there and a metal block being added to change the temperature of the water, how much heat was being transferred from one to another. In this case, the heat that's lost by the metal, if you place a hot piece of metal into colder water, well, that heat that's lost is ultimately heat gained by the water. There's only one place for that heat to transfer if there is no heat being lost to the surroundings. We said that the system is closed. So given that relationship, let's look at a scenario that helps us figure out the identity of an unknown metal. If you have 0.05 kilograms of water at 20 degrees Celsius and you put in a 31 gram or 0.031 kilograms of an unknown substance that is originally at 100 degrees Celsius, you measure that the final temperature of everything is 25 degrees Celsius. What is the unknown metal? So in this case, to find the unknown metal, we're going to calculate its specific heat and compare it to the temperature or to the table that we were given before. So here what we're given is the initial temperature of each of these things. The initial temperature of the water and how hot this metal was before it hit the water. In the end, it all becomes 25 degrees Celsius. That's its equilibrium temperature. The hot thing became colder, the colder thing became hotter. They kind of met somewhere in the middle. So in this case, our first step is to figure out what is the heat energy that is gained by that water, because we know exactly how much water there is, what its temperature change was, and its specific heat. We know MC and delta T. The mass is 0.05 kilograms. The specific heat is shown here in the table. And then the change is it went from 20 degrees up to 25 degrees. Its change in temperature is 5 degrees Celsius. So I can calculate that the heat gained by the water is 1,045 joules. Now, that is going to help us in step 2. We're going to take that heat, 1,045 joules, gained by the water, and say, well, if that was gained by the water, that was exactly what was lost by the metal. So 1,045 joules is equal to the mass of the metal times the specific heat of the metal times the change in temperature. So the mass of the metal is 0.031 kilograms. Specific heat is unknown at first. And then the change in temperature, it was 100 degrees Celsius. Now, when it's in equilibrium with the water, was 25 degrees. So its change was a 75 degree delta. So we can calculate that that was roughly 449 joules per kilogram per Kelvin. I had this highlighted earlier by accident, but you can see if you were to compare that with a list, that most closely matches iron. So by doing a simple experiment, by placing this hotter object in water and seeing how the water changes, we are able to use the knowns to calculate an unknown and help us ultimately figure out from a list what that object is. So some takeaways from this lesson: you should be able to describe and define specific heat capacity with proper units. Remember, those units are really just the definition. It's how many joules per kilogram per Kelvin that object is increasing. You should be able to describe the effect of larger or smaller specific heat values on how fast or slow an object is to heat up. You should be able to relate specific heat capacity to heat energy and temperature change using that Q is equal to mc delta T, and then describe how this calorimeter sort of experiment can use conservation of heat to study a material's specific heat. We will do an experiment like that in a little bit, but just getting that general idea of how to do it is going to be really, really important for this class.